What is an algorithm? An algorithm is a set of step-by-step instructions to efficiently solve a specific problem. Better still, we can say that an algorithm is a set of instructions designed to solve a problem. So you can think of an algorithm like a recipe in cooking. When you want to prepare a meal, you follow a set of steps in a specific order, like gathering ingredients, mixing them in the right proportions, and cooking them at the right temperature. Of course, some recipes are simple and quick, maybe boiling an egg, while others are quite complex and time consuming, like baking a cake. In the same vein, some algorithms run faster and require fewer resources, while others take longer and use more resources. So let's take a look at another example. Imagine you are trying to get to an unknown destination, not having a guide or direction. Sure, this is going to be a problem. However, if somebody provides you with a systematic step-by-step guide, it becomes easy for you to find your way to your destination. In essence, this guide functions just like an algorithm, providing a clear sequence of instructions to help you reach your goal, which is your destination. The two examples I mentioned have one thing in common, which is problem solving. And that is exactly what an algorithm does. Now that we have a clear understanding of the meaning of algorithm, let's take a look at the key characteristics of algorithms. First, a good algorithm is not only correct, but also efficient, meaning it solves the problem with the least number of resources. Once again, you can see it's not just about solving the problem, but solving the problem efficiently. So if you are faced with the problem of getting to an unknown destination, the problem is not just about getting to the destination, but getting to the destination in the least amount of time or distance or even both. And this applies to so many problems. So while it is possible to solve a problem in many ways, the key is to find the most efficient way of solving that problem. And once you have that way of solving the problem, you can present it in a clear, systematic manner so that anyone who follows your approach can as well solve the problem. This is an algorithm in action. In other words, an algorithm doesn't have to be in form of a program. It can be written in plain English. You can sketch it or illustrate it. It can be expressed in form of a pseudocode or even as a computer program. The choice is up to you. However, what really matters is that it provides a clear and detailed procedure for solving a problem. In essence, when you have an algorithm for solving a problem, the problem is as good as solved. And interestingly, algorithms are widely used in almost every industry to solve problems. Whether in healthcare, retail, manufacturing, algorithms play very important roles. For instance, in genetic studies, algorithm can help scientists to understand how genes work. You can use an algorithm to determine the quickest way to a destination. When playing games, maybe in the game of chess, it can provide you with the best move to win the game. And if you visited websites like Amazon or Netflix, you will notice that they offer personalized recommendations. These recommendations are not just random stuff. They are based on your previous interactions with the site. And from these interactions, the algorithm can identify your interests. And from your interest, they will then make book or film recommendations to you. And this brings us to a very important question. Why should one learn algorithm? So maybe you are familiar with programming and you can solve problems using a programming language. The truth is that knowing how to write programs in a programming language is a lot different from solving problems in the real sense of it. If you have a strong understanding of algorithms, you can be able to critically think and solve problems effectively. Also, having a good knowledge of algorithm is what differentiates a professional from a novice. And this is the reason why most technical interviews tend to focus more on problem solving and algorithms than proficiency in a programming language. So if you really want to get professional in a programming language, then learning algorithm is not an option. So now let's look at data structures. When solving problems with algorithms, Data is always at the center. You are either processing data or storing data in one way or the other. But before we delve into data structures, let's take a step back and talk about data types. In programming, data types define the kind of values a variable can hold and what you can do with them. In Python, like most other programming languages, we have what we call the primitive types. These are the building blocks of data. For instance, we have integers, which represent whole numbers. And with integers, you can perform operations or basic arithmetic operations like addition, subtraction, multiplication, and division. Floats are decimal numbers, which also support mathematical operations like addition, subtraction, exponentiation, and the rest. Then we have the booleans, which are typically true or false values, which allows you to perform logical operations like and, or, and, not. These are the primitive types. So these primitive types are very essential, but they come with a limitation. They can only store one value at a time. And this is where data structures come in. A data structure is a way of organizing and managing multiple values efficiently. And Python provides several built-in data structures like lists, tuples, and dictionaries. Lists, for instance, are used to store ordered collection of items, and you can easily modify, alter, update them whenever you need. Tuples, on the other hand, are similar to lists, but they are immutable, meaning that their values cannot be changed after creation. Then we have the dictionaries, which are used to store data in key value pairs. And the interesting thing is that each data structure has its own strengths and limitation. So choosing the right data structure is very important whenever you are trying to solve a problem. When you choose the right data structure, you can be able to efficiently solve that problem. Now, let's talk about the abstract data types, or the ADTs. An abstract data type describes a way of organizing data and the operations you can perform on data. And you don't have to worry yourself about how it is being implemented. So you can think of it as a blueprint on how data should behave. A great example of this is stack. And when we talk about stack, maybe you can imagine a stack of plates. When you have a stack of plates, if you want to add a plate to the stack, it means you have to put it at the top. And if you want to collect a plate from the stack, you collect from the top. So this is what we call the last in, first out. That is LIFO principle. And the interesting part is that a stack can be implemented in different ways. You can use an array, you can use a linked list, but regardless of how it is built, it will always behave like a stack. First in, first out. Other common ADTs include things like queues, maps, trees, and so on. And we're going to talk about this later on in the course. So now that we have a solid understanding of data structures, let's see how we analyze algorithms. But before we do that, we need to know why we analyze algorithms in the first place. The reason is simple: to determine how efficiently it solves a problem. For instance, if you're looking for an algorithm for the route to get you to a destination, you prefer the fastest route or the shortest route. As a matter of fact, when we study or analyze algorithms, we're looking at two main things: how fast it runs and how much memory it uses. First, we want to understand how the time needed to solve a problem grows as the problem becomes larger. Second, we want to check the amount of memory the algorithm needs while it is running. We'll call these the time and space complexities. So by analyzing the space and time complexities, you can tell whether an algorithm is an efficient one or not. Now, how do we really measure the efficiency of algorithms? There are two common approaches to this. One is empirical testing. The other one is determining the running time. Let's start with empirical testing. This involves timing your algorithm to determine how long it takes the algorithm to solve a problem. However, there's a problem with this. The outcome is not always consistent, because if you run the algorithm in a very fast computer, it will not give you the same outcome as when you run it in a slow computer. And this brings us to the running time, which is a better alternative that is independent of the computer architecture. So what is running time? When we talk about the running time of an algorithm, we're focusing on the number of primitive operations required to solve a problem. These are operations like adding two numbers together, comparing two values, or even assigning a value to a variable. But there's an assumption here. We assume that each basic operation like addition, subtraction, memory access, or assignment takes a constant amount of time. This means that assigning a value to a variable, performing addition, or any other basic operation are treated as if they take the same amount of time. This way, we can simply count them, and the sum of these operations becomes the time needed to solve the problem. So this is not a physical time like seconds or minutes, but rather the total number of primitive operations involved in solving that problem. But it doesn't stop at this. Running times are typically represented mathematically. In most cases, running time of an algorithm is expressed as a function of the input size. We can use a variable like n to represent the number of items the algorithm processes and describe its running time in terms of n. This approach helps us to understand how the algorithm performs as the problem gets bigger. This is what we call the growth rate or time complexities. From growth rates, we can determine whether an algorithm is an efficient one or not. So now let's look at some of the common time complexities. We'll have constant time, we'll have logarithmic time, we'll have linear time, linearithmic time, we'll have the quadratic time, exponential time, and we'll have the factorial time and other time complexities. But these are the ones we're going to be focusing on. So let's start with the constant time. Algorithms with constant time take the same amount of time regardless of the input size. A typical example of this is accessing an element in an array by its index or assigning a value to a name. For example, when you access an element in an array by its index, the computer performs one operation, which is getting the value at that position. It doesn't matter how many items in the array, whether it is 1, 10, 100, 1 million, you are performing a single operation. So regardless of the input size, the running time is the same. This is why we call it a constant time operation. Then we have the logarithmic time. And this one, the running time increases logarithmically as the input size grows. A typical example of this is binary search. Then we have the linear time. The running time in a linear time grows directly in proportion to the input size. This means that the bigger the input size, the bigger the running time. For example, if you have a list of items and you perform a loop on it, the number of operations you perform directly matches the number of items in the list. So if you have 10 items, you perform 10 operations. If you have 100 items, you perform 100 operations. Then we'll have another one, which we'll call the linearithmic. This is a combination of linear and logarithmic. So this is slightly slower than the linear time, but faster than the quadratic time. And then we'll look at the quadratic time. And in this time complexity, the running time grows quadratically. And this is usually found in algorithms with nested loops. For example, when you have a nested loop, each item in the outer loop causes the inner loop to go through all its items. This means that if you have 10 items, you might perform around 10 times 10 operations, which is 100 operations. And if there are 100 items, this requires about 100 times 100 operations, which is going to give you 10,000. This way, the number of operations grows roughly in proportion to the square of the input size. We'll have the exponential time, we'll have the factorial time, and so on. So whenever you are choosing an algorithm, especially for large data sets, aim for those with lower time complexities like constant time, logarithmic time, or linear time. And also when analyzing algorithms, we normally consider how algorithms perform in different scenarios. We'll often look at the performance of algorithms in 3 different angles: the worst case, the best case, and the average case performance. And this leads us to asymptotic notations. These are mathematical tools that describe how the running time or performance of an algorithm changes as the size of the input increases. There are three main types of asymptotic notations. We'll have the big O, we'll have the big omega, and we'll have the big theta. The big O describes the upper bound, which is the worst case scenario. The big omega is for the lower bound, which is for the base case scenario, and the big theta provides a tight bound, which is for the average case scenario. Among these asymptotic notations, big O is especially important because it shows us the worst case scenario or the worst case growth rate of an algorithm. And why is it important? Okay, so let's look at it this way. If you want to make an investment, one of the most important questions to ask is the biggest potential risk or loss you can ever encounter. This is the worst case scenario. So if you are comfortable with the risk, you can proceed with investment. In the same vein, if you are choosing an algorithm, it's important that you know the worst case scenario, but the goal is that it never gets to that point. Now you see why the big O is important. So now what we're going to do is that we're going to be using the asymptotic notation to analyze the performance of an algorithm. And we're going to be starting with the big O notation. Of course, the big O gives us the upper bound or the worst case scenario. So we're going to be determining the big O of an algorithm. And to do this, I want you to take a look at this function. We're going to break it down step by step. First, the variable count is initially set to 1, and this counts as a one primitive operation. Then we have a nested loop. The outer loop runs n number of times, and we also have the inner loop which runs another n number of times. So since the inner loop runs n times for each of the n iterations in the outer loop, the total number of operations from this nested loop is going to give us n raised to power 2, which is n times n. So this is what we have for the nested loop. Then after the nested loop, there is also another loop that runs n times, and this contributes to n number of primitive operations. So to sum it up, we have one operation from the initial assignment. We'll have n raised to power 2 operations from the nested loops, and then we have n operations from the final loop. And together, the total number of operations can be expressed as a function of Tn equal to n raised to power 2 plus n plus 1. To find the big O complexity, we'll compare our function Tn to a simpler function Gn, such that if we multiply Gn by a constant C, which is greater than 0, we'll get an outcome greater than or equal to Tn for all n beyond a certain threshold, which is NO. And the first thing we're going to do is to identify the dominant term in Tn. In this case, as n grows, the n raised to power 2 term becomes much larger than the rest, which is the n term and the constant 1. So to express this using the big O notation, we'll compare Tn to a simpler function Gn, which is equal to n raised to power 2. So now we need to find a constant C such that for all n greater than or equal to a given n threshold, which is NO, Tn will be less than or equal to C multiplied by n raised to power 2. Then here's a little trick. We can simplify the expression by rewriting the other terms using the exponent of the dominant term, which is 2. So we can have Tn is equal to, of course, it's n raised to power 2 plus n plus 1. And now rewriting the expression, we can now express all of them in the power of 2. So now we have n raised to power 2 plus n raised to power 2 plus 1n raised to power 2, which is going to give us 3n raised to power 2. For n greater than or equal to 1, we can see that n raised to power 2 plus n plus 1 is less than or equal to 3n raised to power 2, which is the same thing as C multiplied by G of n raised to power 2. Thus, we can say that at c equal to 3, the function holds true for n greater than or equal to 1. And in this case, we can say that our running time is the big O of n raised to power 2. Let's take a look at another example. And in this example, we have a function Tn equal to 3n plus 8. To determine the big O complexity, we'll compare Tn to a simpler function Gn, which is equal to n, and try to find the constant C and the threshold No. So we have Tn equals to 3n plus 8, which is less than or equal to C multiplied by n. So first of all, we arrange the inequality. So we have 8 is less than or equal to C multiplied by n minus 3n. Then we factor out the n, and this is going to give us 8 less than or equal to C minus 3 multiplied by n. Now we need C minus 3 multiplied by n to be at least 8. So if we choose C to be equal to 4, then we can have 1n. That is 4 minus 3 is going to give us 1 multiplied by n, which is going to be 1n. If we then rearrange the expression, we're going to arrive at n greater than or equal to 8. Therefore, we can say that at C equal to 4 and NO equal to 8, the condition for the big O is satisfied. And we can then conclude that Tn is equal to 3n plus 8 is a big O of n. Alright, so let's analyze a more complex function. So we have Tn is equal to 5n raised to power 5 plus 4n raised to power 4 plus 3n raised to power 3 plus 2n raised to power 2 plus n plus 1. As usual, the first thing is to identify the dominant term. And out of all the terms, 5n raised to power 5 grows the fastest. So we can say that Tn, which is equal to 5n raised to power 5 plus 4n raised to power 4 plus 3n raised to power 3 plus 2n raised to power 2 plus n plus 1 is less than or equal to, when we now take the other terms and express them in the exponent of 5, which is 5n raised to power 5 plus 4n raised to power 5 plus 3n raised to power 5 and 2n raised to power 5 plus n raised to power 5. So this means that if we add up these terms, we're going to arrive at 15n raised to power 5. So which means that Tn is less than or equal to 15n raised to power 5. So what this means is that 15 is the constant. So at C equal to 15 and NO greater than or equal to 1, the condition for the big O is satisfied. So we can say that Tn is the big O of n raised to power 5. Next, we move over to the big omega notation. Of course, the big omega gives us the lower bound or the best case scenario. And we're going to express this function in big omega notation. So the first thing we're going to do is to determine the dominant term. And the dominant term here is 5n raised to power 5. Now we need to show that Tn is greater than or equal to C multiplied by a smaller function n raised to power 5. So far we have 5n raised to power 5, and we have Tn is greater than or equal to C multiplied by the smaller function of n raised to power 5. So what this means is that 5 becomes the coefficient, and this expression holds when n is greater than or equal to 1. So at the constant of 5 and n equal to 1, we can confidently say that Tn is always greater than or equal to 5n raised to power 5 for all n greater than or equal to 1. And this is exactly what we need to prove. So T of n is the big omega of n raised to power 5. Finally, the big theta. We're looking at the function again. So this function is still 5n raised to power 5 plus 4n raised to power 4 plus 3n raised to power 3 plus 2n raised to power 2 plus n plus 1. And we've already established that Tn is at least 5n raised to power 5. This is the lower band. And at most 15n raised to power 5, which is for the upper bound. and the big theta is in between the lower bound and the upper bound. And because both bounds are in the form of n raised to power 5, we can now say that Tn grows exactly at the rate of n raised to power 5, ignoring the constant factors. So this means that T of n is the big theta of n raised to power 5. Before we conclude, let's look at algorithm designs. Algorithms can be grouped into different categories based on how they work and what problems they solve. We can group them under these 4 categories. We have the divide and conquer, greedy, dynamic, and backtracking algorithms. The divide and conquer algorithms break a problem into smaller subproblems, solve each of the subproblems recursively, and then combine the results. This is commonly used in algorithms like merge sort and quick sort. The greedy algorithm picks the best option at each step, aiming for the overall best solution. It works well for problems like finding the shortest path in a graph or data compression, but doesn't always find the perfect answer. Then we have dynamic programming, which solves problems by breaking them down into smaller repeating subproblems and storing their problems to avoid doing the same work multiple times. This method is useful in problems like calculating Fibonacci numbers and finding the shortest path in a network. Finally, backtracking tests different solutions and reverses choices when they lead to a dead end. It's often used in puzzles.